Okay, this is number 4 on the practice exam. It's asking us to find y of t for the LTI system if its impulse response is given as h of t when the input is x of t. H of t is equal to e to the minus 2t times the unit step, and x of t is the unit step minus a shifted unit step. So right here is the definition of convolution, and because it's commutative, we can also write it as that. So this is actually going to be the form we're going to use for this problem. You could do it with this version, but I think it's a little more difficult. But if that's more intuitive to you, go for it. As long as you end up with the correct answer, it doesn't really matter how you get there. So let's first write formal definition from here. So it's going to be equal to minus infinity to positive infinity h of tau times x of t minus tau d tau. Okay, so now we need to figure out what these functions actually look like. So x of t is just going to be a rectangular pulse of width 2, and if you don't know how I got that, go ahead and go back and watch the previous videos. I believe I derived this in the video on transformations, so you can find that there, or you can work it out. If you don't know why that's true intuitively, you should probably spend some time figuring that out, because that will save you a lot of time and grief. So now we need to find x of t minus tau. So this is going to be a variable change and a shift to the right by t. So when we're dealing with a transformation like this, we're always going to shift first. In this case, we're also going to make the variable change at the same time. So this is no longer the t-axis, it's the tau axis. And we are going to shift to the right by t. So this is going to be t. The signal width is 2. So this is t plus 2. The fact that I drew it across the axis is just arbitrary. I think it makes it a little easier to look at, but you could have drawn it completely over here. I think you just would have trouble reflecting it, maybe. So this was x of tau plus t. So now we need to find x of minus tau plus t. So now we just reflect this. This is the tau axis, so this is going to be t minus 2 here, since we're reflecting it. This is why I think it makes it easier to look at. This is going to be t, just amplitude 1, of course. I didn't put that up here. Okay, this is x of minus tau plus t, and h of tau is just a decaying exponential, and it looks like this, something like this. We don't really need its exact graph, because that's just not how we're going to do it. And h of tau is equal to e minus 2 tau times u tau. So, of course, no matter what this part was, h of tau is only going to be valid for values t greater, or tau greater than 0. Okay, so now we can start. The integral, again, was minus infinity to infinity of h of tau times x of minus tau plus t d tau. Okay, so we need to split this integral up, and we're going to consider different cases. So for case 1, t is less than 0. When t is less than 0, x of minus t plus tau does not overlap with h of tau, and h of tau is 0 for values of tau less than 0, and since t is less than 0 and t is just a point on the tau axis, this integral is just going to be 0, because any integral with an integrand of 0 evaluates to 0. So what that looks like practically is minus infinity to t, whatever t is, with the stipulation that t is less than 0, is going to be h of tau times 0. Sorry, I wrote that backwards. It's going to be x of minus tau plus t, which is non-zero for values of tau less than 0, times 0, which is the 0 is representing h of tau here, because h of tau is 0 for values less than for values of tau less than 0. So this equals 0. Hopefully that didn't confuse you too much. So our second case is going to be when t is greater than 0 and t minus 2 is less than 0. So you can imagine this has shifted over, and we definitely have some overlap of these two signals. We don't know quite what it is, but we have some overlap, and we can solve this analytically quite easily. So in the area of overlap that we do have, that overlap is going to be from tau equals 0 to t, whatever t is. So the amplitude there of x of minus tau plus t is just going to be equal to 1. So we can just evaluate the integral of h of tau, and that looks like this. So we're going from 0 to t, and x of minus tau plus t is again just equal to 1. H of tau d tau. So this is 0 to t times 1, and h of tau has a unit step in it. but the unit step for values of tau greater than 0 is just equal to 1. So we can just write that as amplitude 1 here as well. And then we have our decaying exponential, d tau, and that's going to be equal to minus 1/2 e minus 2 tau 0t, and that is equal to 1/2 1 minus e minus 2t. So that's case 2. Okay, so now we need to consider the last case, case 3 for this, and that's the case where we know t is greater than 0 for sure, and we also know that t minus 2 is greater than 0. So in the width of x of minus tau plus t, which is 2, we have complete signal overlap. So we can solve this integral analytically, similar to what we did before. The lower limit is going to be t minus 2, because to the left of t minus 2, x of minus tau plus t is equal to 0, so we don't need to consider that. And our upper limit is going to be t, because to the right of t, x of minus tau plus t is also going to be equal to 0, so we don't need to consider that area either. H of tau here is just going to be equal to the decaying exponential, because the unit step is 1 for values of t greater than 0, and we for sure know that we are at values of tau greater than 0. This looks a little awkward to write, but there's nothing wrong with this statement. They can definitely both be true. And if you're not sure why, stop and think about that. Okay, so we just have e minus 2 tau, d tau, and we get minus 1/2 e minus 2 tau, and limit's going to be t minus 2 and t. So when you evaluate this, you are going to get it equal to 1/2 e minus 2t times e to the 4th minus 1. Okay, so now we have all of our separate cases, so we can write what the output y of t for the LTI system is going to be. And it's going to be equal to 0 for values of t less than 0, and it's going to be equal to 1/2 for 1/2 times 1 minus e minus 2t for values between t greater than or equal to 0 and less than 2, and it will be equal to 1/2 e minus 2t e to the 4th minus 1 for values of t greater than excuse me, 2. Okay, So that's number 4. This was a long video. Definitely don't just watch this video and think that you've got it down. You need to do this problem by yourself and make sure that you can recreate this, because you're definitely going to see this on the exam, and convolution is probably arguably one of the most difficult topics you'll see in this class, and probably one of the more important ones, so you definitely want to get this down. Okay, thank you, bye.